Today we're going to look at residuals in this video one step further. So how can we use a residual? So the question is, what are the bounds of our prediction? So we're going to use residuals to find the upper and lower bounds of our prediction. Let's pretend we are in an archaeological dig. So we're digging up some ground and we find what appears to be a forearm bone. It's kind of human-like, so we'll say it's not human, but it's a humanoid-looking bone. Now we have no other bones, and we want to think about what would maybe be how tall was the humanoid that had this forearm bone. So to answer that question, maybe we take the class or people around us and we measure their forearm bones. So from their wrist to their elbow, we measure that forearm and we also find their height. And we kind of have this table of data that would correlate to those people. So the first question is, what should we report about the data? This is a question about the data itself. So if we look at this data, the data points, they're kind of in a not straight line, but they're trending in a linear fashion. There's no curve there. So we would say that the data is linear. It's positive. So as the forearm length increases, the height increases. So we have an increase. So we might say the data is positive. We'd also say this data is moderate. We're comparing the data to that line of fit. So because it's not really scattered around the line and it's not really close to the line, meaning all the data points aren't really close to the line or all the data points aren't really far from the line, we would call this a moderate, have a moderate strength, because it doesn't have those extremes. And then we would also state there's no outliers to this data. There's nothing that's really off the charts or skewing this data away. So the first thing we want to do is we want to find that model equation, which we have been calling it, the prediction equation. So we want to find that prediction equation. So I want to find the slope and I want to find the y-intercept of this line. We'll start with the slope. When we draw lines of fit, we try to put them through at least 2 points to make it easy to find the slope of the line. However, in this graph, we don't have our line through 2 points. So what we're going to do is we're going to add 2 points to our graph just to help us find slope. These aren't data points. These aren't very special. They're just 2 points on the graph that would help us determine the slope. So the first one I'm going to put is this point right here. And the second one I'm going to put is at 25. Kind of hard to see. It's right about there. The point for the 22 this would be 150. So it's right below that. So I'm going to call it 149. And then the point for 25 is slightly above. I'm going to call it 161. Now, again, these aren't data points in the data. They're just points on the line to help me determine the slope of that line. So I'm going to go ahead. I'm going to use my slope formula here. So I have y2 minus y1. So I'm going to do 161 minus 149 divided by 25 minus 22, which is going to give me 12 over 3 with a slope of 4. So that's going to be the slope of my line. So I'm going to go start that. Y equals 4x. Now, when we talk about the y-intercept, this graph is kind of tricky. I'm going to slide it up here so you can see everything. This graph is at 20 on the x-axis, not 0, which means this line here is not the y-axis. So we have to be pretty careful there. We do have to be pretty careful. So what we're going to do is we're just going to do a little bit of math. If I am at 20 and I have to go back to 0, that's a change of 20 times backwards, and the slope is 4. So I'm going to subtract 4 20 times, giving me a total of 80. So I'm going to take this value point, which I'm going to call 141, and I'm going to subtract 80. So 141. So essentially I'm saying, all right, if this kind of continued, where would it be at 0? And it would be at, that's a bad y-axis, it would be at 61. That would be the y-axis if we continued back. So my y-intercept is 61. Now the question is, what's the furthest residual? So looking at the graph, when we talk about what's the largest or furthest residual, which data point is farthest from the line? And that's going to be this point right here. That is the furthest point from my prediction line, which means it's my furthest residual. Positive or negative doesn't matter. It's just which is the furthest from that prediction. So that correlates with an x value of 24. So that I'm looking right here in my data table, and you can't see that, so I'll slide it down. I'm looking right here at 24. So what I need to do to calculate the residual is I have to know that prediction point. So in our last lesson, we talked about I need to take my prediction equation, 4 times my x value, which is 24, plus 61, which gives me 157. So again, that's my predicted value. My actual value is 175. So this point is 175. This point is 157. So if I calculate my residual as actual minus predicted, my residual will be equal to 175, the actual data point, minus what we just got with our prediction equation, giving us a residual of 18. So the distance from the prediction line to this furthest point is 18. All right, so that's what we want. So that's going to be an important part here. 18, our furthest residual. So at the beginning of the video, I mentioned bounds, upper bound, lower bound. What does that mean? Well, I'm going to draw something on here. I'm going to draw something on my graph. What I'm going to draw is I'm going to draw a line that is parallel to my line of best fit. So I'm going to do my best to make this parallel. I think that's pretty good. And it goes through that point. And it goes through that point. So there it is. That is my line through my furthest residual parallel to my line of fit. This is going to be called our upper bound. It's kind of like the upper limit of our predictions. We're kind of saying like, this is like the cap of our predictions. We can say up to this line. Now it's made through that furthest point. So what we're going to do is we're going to take this line and we're going to reflect it over our line of fit, meaning we're 18 above this line. We're going to go 18 below this line. So we said this was 157. So 157 minus 18 is 139. So I'm going to put a point as best as I can about 139. And I'm going to make another parallel line through that point we just kind of created ourselves. This is called, notice it's still parallel. This is called the lower bound. This is the lower bound. And again, it's also 18 away. It's also 18 away. What we're stating here is something unique. We're basing the distances of these two boundary lines on that furthest residual. So we're in the scheme of things, we're taking the furthest data point, the furthest actual data point And we're saying like, okay, that's the furthest one away. So everything that we're talking about should maybe only go up to that point, and then maybe below our prediction to like that same distance. We're saying our predictions, we're confident in our predictions if they fall within this boundary points or these boundary lines. So let's talk about the equation for these boundary lines. So I'm going to first start with the lower boundary. The lower boundary line is parallel. Because it's parallel, it has the same slope. So y equals 4x. The slope is not going to change because it is parallel. So our upper boundary will still have the same slope, y equals 4x. Now the question becomes, what's the y-intercept? Well, the y-intercept, to shift a line up or to shift the line down, we're changing where it crosses the y-axis. We're changing that intercept. So if I changed this line 18 up here, that means the y-intercept would also shift 18 up. So if I take my 61, y-intercept of 61 for the line of fit, now remember this isn't the y-axis, but it's to demonstrate it, I would add 18 to find out where it would be on the y-axis. So I'm going to take 61 and I'm going to add 18. Now I made the mistake here that we're talking about the upper boundary. So I take 61 and add 18. I end up with a y-intercept of 79. So again, this is coming from 61 plus 18. Now, if I want the lower boundary, I'm taking that y-intercept and moving it down 18. So 61 take away 18 is 43. And again, that's coming from 61 minus 18. A very common error is students want to put minus 18 and plus 18 here. But remember, we're manipulating that y-intercept in order to find those new y-intercepts for our boundary equations. So the lower bound equation should have a y-intercept that's below our line of fit, and the upper boundary should have a y-intercept that is above our line of fit. All right, so how do we use this? Prediction using bounds. All right, so we want to predict using bounds of 20 for the bounds for 26.4 centimeters of length. So if I use my equation, 4x plus 61, that was the prediction equation, and I substitute 26.4. The prediction is 166.6. So we're predicting that height of the humanoid. Now, from there, I'm going to go up 18. And that would give me an upper bound of 184.6. So that's like the upper limit of our prediction. And for the lower bound, I would subtract 18. Because remember, that was based off our furthest residual. So our lower bound prediction, the lowest prediction is 148.6. So we would pretty much say our prediction is this, kind of give or take 18 centimeters. We could also find these bounds by plugging in 24.6 into the upper equation. That would give us this value. Or we could plug it into the lower bound equation for this value. And that is upper and lower bounds.